Hi, this is Professor Fernandez, and this is video 3 in lesson 16. This is a video that starts a new chapter in the book that we're using, Calculus Simplified. And the topic here is accumulated area and also viewing distance as area. So example 5.2 is the one that I'll be going through here. Let's see what it says. An object's instantaneous speed function is s of x equals 1 plus 2x, graphed in black in figure 5.2 over here. Okay, and then part A, calculate A of t. This is the area under the graph of s of x over the interval 0 to t. So just to give you a preview, what this example does and what's done before this example in the book, in the beginning of chapter 5, is again relating distance traveled to area and thinking about accumulated area specifically as a way to relate that distance to area. This part A might seem like it has nothing to do with those topics, but we're getting there. Once we do B and C, we'll see those connections in this example. So part A, calculate that area under the graph of s of x over the interval 0 to t. I'm going to zoom in here. That is the area of this blue shaded region. And we can do this just using geometry, right? So this is the area of a trapezoid, okay? So the area here, area equals 1/2 the base, which is this length here of t, times the sum of the heights. So that's 1, and that's 1 plus 2t on this side, right? So it's this height, 1 plus 2t, and it's this height of 1. So 1 plus 2t, right? So again, this is the first height over here, and this is the second height over here, using the area of a trapezoid formula. Okay, great. So let's simplify this here. We get 1/2 t, and then add these. You get 2 plus 2t. Factor out the 2, 1/2 times t times 2, 1 plus t, and then cancel out the 2's. So I get t plus t squared. So that's my a of t that I'm going to put over here for part A. A of t equals t plus t squared. Okay, so if I had a magic wand and I could animate this figure on the right, we would see the nice property of thinking of this a of t function as accumulated area. So I don't have a magic wand, but I do have this nice ability to draw this over and over again, right? So let's say t is over here, then this is the accumulated area. What if I increase the t value a little bit over here? Right, then I would sweep out this accumulated area. So you can see that as t increases, right, I sweep out more and more area. So you can think of this area up here as being something that accumulates, right? If I move t over here, I accumulate more area. Move it over here, I accumulate even more area. And visually, what we keep seeing is a trapezoid that increases in size as t increases in value. Functionally speaking, the area of that trapezoid is given by this function. So we can actually calculate the area without needing to go back to that geometric viewpoint anymore, without needing the trapezoid. So that's nice. Let's look at part B. So calculate a prime of t, and then verify 5.1 by repeating the calculation that led up to it. Okay, let's do the part first that we can do first fairly quickly and easily. Calculate the derivative. So this is a sum of power functions, so I'll differentiate it using the power rule. Derivative of t is 1. The derivative of t squared is 2t. So 1 plus 2t, right? That's a prime of t. And then verify 5.1. So what is 5.1? I've put it down over here. This refers to formula 5.1 in the textbook, which says that the derivative of the area function, the accumulated area function, a of t, is equal to s of t, which is the instantaneous speed function where I've replaced x by t. And you can see that that's exactly what happened here. So s of x is 1 plus 2x. S of t is 1 plus 2t. So we have verified 5.1. Great. And then it says, by repeating the calculation that led up to it. So this refers to a calculation that I did in the book, which started from this very simple definition essentially of the derivative and ended up over here at 5.1. So I'm going to do that verification here, right? What I've just done here is I calculated the derivative, I got something, and I related it to the s of x function, the instantaneous speed function that we had. So I verified this formula 5.1 in that sense. Now I'm going to verify it in this sense, right? So I'm going to go back to a of t, sorry, a prime of t, and I'm going to use this definition. Limit as delta t goes to 0 of delta a over delta t. And I'm going to write that out. So that's a of t plus h. Oops, and I'm using delta t. So a of t plus delta t minus a of t over delta t. Right? So the point of doing this is to show you that, we can again think of setting up a nice correspondence between the picture up here of the blue shaded area and thinking of as t changes, right, I accumulate more area, and that changes the value of the area, right, because this is a function of t. It should change, it shouldn't keep it constant. But what if I just, move to t plus delta t, a very small area in t? Okay, well, what would this red colored area represent? Well, this is a of t plus delta t. Remember, that's the area of the entire new trapezoid, minus a of t. That is the area of the blue shaded region. And then if I divided by delta t, if I divided this red colored area by the length of this delta t, right? And I took the limit as delta t went to 0, well, on the one hand, I get a prime of t. On the other hand, if I zoom in here and you can see as delta t gets smaller and smaller and smaller, what I end up getting is something that's very, very close to t, right? And if I just look at this area and I divide by that, I'm basically going to get like this line, And the area of this line is a strange thing to think about, but the area of this line is like a rectangle. It's like a rectangle with a very, very small width and a height of 1 plus 2t. So we expect the 1 plus 2t to show up here, right? Which is what we're getting with a prime of t. So that's kind of, very quick review of the intuition behind this. I definitely recommend that you read through the beginning of chapter 5. It's a few pages where I explain this in detail to make this connection and set things up. To finish the example here, let's actually do the math. So let's calculate the limit as delta t goes to 0. A of t plus delta t, I'm using this a of t here. So I'm doing t plus delta t plus t plus delta t squared. And then I'm subtracting a of t, which is t plus t squared. Subtracting that. And I'm dividing by delta t. Okay, so then I'm just going to simplify the numerator here. We see that in this part of the numerator, I can square things out. I get t squared plus t delta t plus delta t squared. And then this t cancels with this t. Great. And then this t squared cancels with this t squared. So what's left in the numerator, delta t goes to 0. We have a delta t down here. We have this delta t, right? That's one of them. So that's delta t. And then we have this next term plus t delta t. And we have this next term plus delta t squared. Okay, remember these two canceled, and so did that one. And you can see that all of these terms have a delta t, so I can pull one out of the numerator and factor one out and cancel it with the denominator. So I get rid of this, this, and this. And I'm left with the limit as delta t goes to 0 of 1, because I canceled that with that, plus t, because I canceled that with that, plus delta t. Okay, great. So at this point, and I should have mentioned that there's a 2 over here, 2t delta t, coming from the square here. So that puts a 2 over here, and that puts a 2 over here. Okay, great. So then at this point, I am left just taking the limit of this, which we can see is 1 plus 2t. And that is indeed s of t. So again, this is a different way of showing what we did initially much quicker, but hopefully with the pictures that I drew a few minutes ago here, you saw how intuitively speaking, we would expect that this derivative would actually equal the y value, which is 1 plus 2t, right, at t, which is as delta t goes to 0, what you expect in terms of this trapezoid that I drew, getting closer and closer to this functional value at that x equals t. Okay, and then the last part of this calculation of this example here, part C, what does that say? So it says calculate the object's distance function. This is another point where, I will refer you to chapter 5 in the book. The distance function, it has the property that its derivative is the instantaneous speed function. We in part B just showed, verifying equation 5.1, that s of t is equal to the derivative of the area function. So therefore, a prime of t equals d prime of t. D is again the distance function. So I can, use a very similar argument to what I do in the book. If I just move things around here, and I put the d prime of t on the left-hand side, right, minus d prime of t equals 0, and I use the properties of derivatives. A difference of derivatives is the derivative of the difference, right? Then, I refer you to the book for the details, but what's happening here then is that this is a function, let's call it capital F of t, whose derivative is 0 for all t values. And a of t is continuous, right? It was t plus t squared. S of t is continuous. Everything is continuous. So we expect from here that the function itself is 0. If you think of a function whose slopes of the tangent lines at any t value is 0, that's what this is saying, then it's really hard to think of a function that is not 0 with that property. It could be constant, right? So it could be maybe not 0, but it could be 7 or 29. There are ways to argue that it should be 0. And the way to argue that in this case is to think about what f and f of t represents. It's an area minus a distance. And we know that at t equals 0, for example, if you haven't moved, then you haven't covered any distance. So d of t equals 0 is 0. Also, if t is 0, remember our formula for a of t, t plus t squared, right? If t is 0, a of 0 is also 0. So we know that this function f of t has to be constant. Its derivative is 0. And we also know that at t equals 0, the value of the function is 0. So that tells us that the constant must be 0. All right, so I've kind of explained more in some sense than I wanted to, because I did want to refer you to chapter 5 to read more about the details of how this works. But the point of this explanation has been to convince you that the area, the accumulated area function a of t, is actually equal to the distance function d of t. So this is a really, really nice result, and it's why I talked so much about this at the beginning of chapter 5, and why I'm doing this video, because this is geometric, this is mechanics, this is physics. So distance and area, and here they are being equal to each other. So to finish the example, it says calculate the object's distance function. Well, now that we know that in this example, the distance traveled is equal to the accumulated area, and in part A, we calculated the accumulated area to be t plus t squared, then d of t equals t plus t squared. So that is pretty cool. Again, this is the start of chapter 5 in this book and in this course, which is talking about integration. So up to now, we have talked a lot about differentiation in the course and its applications. This is the first time where we're using that, right? This is a derivative to start shifting the perspective. Rather than give me a function, calculate its derivative, now I'm kind of going the opposite way, right? Give me the instantaneous speed. Give me the derivative. Right? Give me the derivative and let me calculate the function. That's what we effectively did here. We had information about the derivative, which we were given. This is the derivative d prime of t. And we use that information to calculate the function it came from. which is t plus t squared. We'll do much more of that in the subsequent videos in this chapter and in the remainder of the course.